here. Today I'm going to go ahead and demo my statistical language modeling code, and as you can see I'm on the supercomputer M3, so let's get started. Okay, so my code is actually all stored in this corpus reader slm.py, which I'm going to turn in, and this has bigram generate as well as all the helper functions for calculating probability and so. But I thought it'd be nice if we could go together step by step to demo the code, and that's why I put it into a Jupyter notebook. So here's just some basic setups and imports. And then here's where I actually load my corpus reader in, so that's where that's coming from. And then we have 10 different articles in here, and each of them, here's the titles of them and the word count. You can see they're all between 50 and 100 words. And then here's just some information about how they're tokenized, as well as a little bit of a preview of 3 of them, just so you can see what's in them. And then now we're actually going to begin building the SLM. So as you can see over here, toStem, smooth, and trigram are all set to false, and it's going to calculate the top 10 unigrams and top 10 bigrams. But you're about to see why you actually don't want smoothing set to false. So here you can see the bigrams. There's just so many of them, way more than 10. And also, we've counted punctuation as their own words, so that's why you see some that are like recognition comma instead of 2 words. But the reason it does this is that when smoothing is turned off, the probability of a bigram is just the count of the pair divided by the count of the first word. So this means that every bigram that has ever appeared gets some probability, and many of them tie with the exact same value. So the list ends up showing a huge number of bigrams. When I turn smoothing, Laplace smoothing on, the denominator grows, and the ties get broken. So the top bigrams shrink down to the actual ones that occur more often, and I'll show you that right now. There we go. So now you can see the actual probabilities and the top unigrams, comma, period, and R, etc. Then top bigrams, comma, and amounts of, and environmental, etc. And so I'll go ahead and show you the actual generation now. So there's code 0, code 1, and code 2. Code 0 is the most strict, because it always chooses the word with the single highest probability compared to the last word. So if there's a tie, it just picks randomly between the tied words, and that makes the sentences repeat themselves a lot because the model never explores less likely words. So I'll show you that. And you can see it often repeats environmental sustainability, or like words that start with environmental, since it's pretty high up on the list. Let me see if I can, again. Yeah. So like right here, for example, environmental sustainability in many regions worldwide, and environmental interference and environmental stress. So then code 1 is the most flexible. It samples words according to their probabilities, kind of like rolling a weighted dice, where common words still show up more often, but rare words can slip in sometimes, which gives you a lot of variety. So governments worldwide are revolutionizing rocket technology. Companies are extremely sensitive to improve urban services and auto. So it's definitely more out of pocket, but sometimes it's a little hard to understand. And then code 2 is a really good middle ground, and it tends to be a lot more cohesive because it looks at the top 10 most likely words and then it samples among them. So this avoids weird rare words from showing up, but it's also less repetitive than always picking the top word. So here we have hydroelectric power in major corporations worldwide. Work. AI also raises important questions about job displacement. So yeah, so we'll go ahead and do a deep dive into the code right after this. Thank you. Really quick, I also wanted to show unigram generate and trigram generate. So I'm going to go ahead and run this. And you can see it generates and over and over, since that's the only word in top probability for code 0. For code 1, it's able to choose some other words that aren't just the top 1 or top 10. So you can see, and then for code 2, again, it has to choose from that top 10. So it also doesn't make sense. Yeah. And then for trigrams, I'll demo this. They should be a lot better. So even for code 0, you see energy sources are reshaping the global energy landscape. There's a couple of repeats, but definitely better than bigram and unigram. Code 1, yeah, same thing, where it can choose other words, but it looks pretty good. And then code 2 looks the best. Like, for example, gene editing technologies like advanced batteries are solving the intermittency problem of renewable resources or sources. So yeah, that's that. Storing the probability, right here is where I actually count the raw counts of unigrams, bigrams, and trigrams. And each counter maps an n-gram to how many times it appears in the corpus. And then right here, right under that, for sent in, In this loop, I basically update the counters. So for every sentence, I add word counts to the unigram counter, pairs of words to the bigram counter, and triples of words to the trigram counter. So if the trigram mode is on. And these are just counts, not actually probabilities yet in here. So then if you go down right here, this is where I calculate the total number of unigrams and keep track of the vocabulary size. So these numbers are important for converting counts into probabilities and for smoothing. Then I go down right to unigram probability, and over here, this is how I actually store the probabilities. So I don't pre-calculate them, like I'm not actually storing the probabilities, but I calculate them on demand. So for example, if the unigram probability, it's just like the count divided by the total words. Without smoothing. But then when smoothing is on, I add 1 to every count and adjust the denominator. So that's Laplace, and then there's the bigram and trigram probabilities over here. And so the same idea works for this. So like if I take the count of the pair and divide it by the count of the first word and apply Laplace if needed, this way the probabilities are accessible without needing a separate table. So basically I store the raw counts in the counters and then calculate the probabilities using helper functions. Bigram generate function, and it builds a sentence one word at a time based on bigram probabilities. So the code parameter controls how the next word is chosen, again 0, 1, or 2. And then over here we have setting up the sentence. So basically if you give the function a head word, it starts with that. So like if you give it like it'll start with the dog, blah, 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 blah. Otherwise it starts empty. And so I also limit sentences to 30 words max so they don't go on forever. So then the first word comes from get start words. So if it isn't provided a head, then it picks a random sentence starter from the corpus, or it falls back to the unigram probabilities to pick one. And then this ensures every sentence has something to start with. And then here is the main loop over here. So basically this loop, when the loop begins, it looks up all the words that can follow the previous word using the next by bigram function. And for each possible next word, we calculate the probability with bigram probability. And then only obviously keep the candidates with a non-zero probability. And then there is stop if there are no more candidates right here. And then for choose next word right over here. Otherwise you choose the next word from the candidate list. And that's like also the 0, 1, or 2. And then check for end token. So if the chosen word is a punctuation mark, period, question mark, or exclamation, the sentence stops. And then of course these like exclamation points and stuff are like set as words. So if that's generated, then it will stop. And then there's also like return self-format sentence, which this just returns a full sentence formatted with correct spacing. And that's it.